So we have covered some implementation details in the MapReduce system. Next, we will talk about some refinements to make the system run better and faster. And the first refinement will be about the combiners. As you may recall, usually a map task will produce many pairs of key value pairs, and some of them may turn out to have the same key. For example, in the word count task, we may have a lot of popular words like the or and sometimes even in a single document, you may have 1,000 pair of of key value pairs with the same key there. And you note that the map task will distribute all these pairs into several different reduce tasks. So this is very expensive network communication. And we can save this network time by actually pre-aggregating the values inside this map task. And this is basically doing the same thing as the reduce function, just you're not doing it in the reduce node, you're doing it in the map node. And back to the word counting example, and more concretely, if you look at this figure, you can see that the mapper will just map the input key value pair into some key value pair with the key B, C, D, E, D, B, and the values that all of them are 1. And the combiner will just pre-aggregating things. Like, for example, we have 2 key value pairs that are exactly the same, B and 1. So it's going to combine these two into one single key value pair. And this is done before the shuffling and group by key operation. And once this is done, the result will be shuffled and grouped inside the reduce node, and it will be pushed to the reducer to do further processing. And in this way, much less data needs to be copied and shuffled, and it's way more efficient. And often, this combined function, like we said before, it will be almost the same as the reduce function. The input of the combiner would be the key and the list of values, and the output will be just the values. And in the word count example, you will just take the list of the values and sum them up. And one caveat is that the reduce function is supposed to be commutative and associative for this to work. And commutative means that, for example, in the sum operation, 1 plus A plus B should be the same as B plus A, and associative means that A plus B plus C should be identical to A plus the sum of B plus C. Now, more concretely, if you satisfy this condition of commutative and associative, then in a large chunk of document, you can split it into small chunk, and you can do a sum operations here, do another sum operation here, and sum the results of these two operations to get the final result. So this series of operations will get the same result as you sum them all up. Now, what if this operation does not satisfy the commutative and associative property? One example is the average operation. We can see that although it satisfies the commutative property, it's actually not associative. Now, if you do an average operation on the first chunk of the data and do another in the second chunk of data, and you average the result of them too, this will be a disaster because it will not gonna be the same average number of what you get from average all of them directly. So how are we gonna address this problem? As it turns out, there's a trick that you can use to circumvent this situation. You can notice that the average is actually the sum divided by the count, and both the sum and the count are actually commutative and associative. So by observing this, you can do a operation to calculate the sum and the count for the first chunk of the data, and also for the second chunk of the data. And you do another sum and count operation on the result of these two. And then you just like get the final sum and the final count and divide them to get the final average number. Unfortunately, there are some operations that are actually hopeless. They are not commutative and associative, and there's no workaround. For example, median. And in fact, you can mathematically prove that there is no effective combiner you can write for the median operation. And besides the refinement on the combiner, there's another refinement on partition function. As you recall, the partition function is actually just a hash function to hash the key in the key value pairs to some reduced workers, right? And it will ensure that the key value pairs with the same key will always end up in the same reduced worker. And usually the system will use a default partition function, which is something like this. We hash the key and modulo by R, and the same key will end up in the same reducer. And this is good for load balancing. But sometimes it's actually useful to override this default hash function. For example, if you want the results from the same host to end up in the same output file or end up in the same reduced worker, you can do something like this. But instead of hash the URL itself, you can choose to hash the host name of the URL. That way, the result of the URL of the same host will always end up in the same reduced node. Now, we have talked about most technical stuff about the MapReduce system. Now let's turn to some applications or problems that are suited for MapReduce. One example is the computation of host size. Let's suppose we have a large web corpus and we can look at the metadata of the web pages in such form, like we can have the URL of the web page, we have the size of the web page and the date, etc., etc. And the task is that for each host, we want to find the total number of bytes that are stored on this host. That is the total number of page sizes for all URLs from that particular host. This is because for one host, there might be several URLs, right? And this is actually very easy within the MapReduce framework. For the map function, you can just like calculate. The only function that you actually need is to extract the host name of the URL. And then the key would be just the host name of the URL. And the value, of course, would be the page size inside this URL, right? And the reduce function is similar. In the reduce function, we can just sum up all the page sizes inside the key value pairs with the same key. Another example is actually related to the host size, which, for example, you might use this kind of result as intermediate result to further develop other MapReduce tasks for link analysis, graph processing, or any other machine learning algorithms related to graph or web mining. And another concrete example would be in the language model. Sometimes it will do something on statistical machine translation, and you might need to count the number of times every 5-word sequence occurs in a large corpus of documents. And how do we do this? This is still very easy for MapReduce, because in the map function, you only need to extract some key value pairs like this. So the key would be the 5-word sequence, and the count would be usually it's just 1, because you are reading the document sequentially, right? And for the reduce function, you just combine counts. So this is very straightforward. And until now, we have finished all the technical content on MapReduce. And a fun fact is that this MapReduce system is actually first proposed by Google and used by Google in the Google file system. And later, Hadoop is actually an open source implementation of the version in Google, and then it's written in Java. And it uses HDFS for stable storage. And you can download the whole package here. It's in Apache package. And since most operations in the MapReduce system on the data is actually very similar to the SQL operation. So there's actually a cluster optimized SQL database that also implements the MapReduce. And this is called Aster data. And besides setting up your own cluster of nodes, you can also choose to run the MapReduce task on the cloud. And by running it on the cloud, you get additional services like persistent storage. One example is that you can run it on Amazon's Elastic Compute Cloud, which is also known as EC2. And Amazon, of course, it also supports persistent storage that is implemented using what they call simple storage service, which is S3. And note that both the Aster and Hadoop can be run on EC2. And in Amazon, they even implement a MapReduce version on the EC2. That's called Elastic MapReduce, or EMR. And if you want to read even more about MapReduce, you can go through some blogs and papers that are provided here. And there's also some source code if you want to dig deeper into it. And one last thing is that Homework 0 will soon be released. And this is just a Hadoop tutorial that you can use to set up the environment and do some simple tasks. And this is a practice homework, so it will not be graded. And this homework should take you about 1 hour to complete. And this is the toy homework to get you started. So be aware that the real homeworks that are behind this will be much more challenging and takes longer. And you can check announcement on the Canvas and the course website for any updates.